when we discuss heart rate and performance, typically we're looking at the heart rate's response to a submaximal load rather than a maximal load. So if we have a look at this figure, we've got a runner at 14 kilometers an hour in the x-axis with an associated performance heart rate of approximately 145. If the treadmill is increased to 15 kilometers an hour, we see an associated increase from 15 kilometers an hour to 155 heart rate. And then similarly, a linear response at 16 to 165. So we describe the relationship between running velocity and heart rate as, roughly speaking, linear, i.e. a straight line. When the athletes run on the treadmill or in the field, they often will wear a watch. The watch gives you heart rate. So heart rate is only one of the two variables that actually contribute to your cardiac output. So your cardiac output is the total volume of lovely oxygenated red blood cells being delivered to the working muscle. So as the rate increases, the delivery increases. That's only one component. The other component is stroke volume. So the stroke volume is the volume of blood that the left ventricle pumps on each one of those individual pulses. So it's a product of rate times volume, which will give us our cardiac output. So in terms of performance, we might say the cardiac output in this instance gives us the capacity to run at 18 kilometers an hour. In this illustration, we've got a cardiac output on the left, which exceeds that on the right. If you have a look at the rate, it's the same for both picture A and picture B. So we've got an equivalent heart rate, but the stroke volume has gone down. So something like that happens maybe with dehydration or something like that, whereby the left ventricle pumps out a smaller volume. So in this instance, if the stroke volume goes down, that means that the total cardiac output goes down and the 18 kilometer an hour velocity can't be sustained. In this figure, we have a cardiac output, so the product of rate and stroke volume, which is equivalent with an alternate rate and an alternate volume. So athlete A has the same cardiac output as athlete B, but athlete A has a lower rate and a higher stroke volume than athlete B, who has a higher rate and lower stroke volume. So they both have the exact same amount of blood being delivered by the left ventricle to the working muscle. However, if we were to maybe take a race circumstance where, in this instance, there's equivalence in their cardiac output, but the velocity was to increase. If both athletes, let's say, had a maximum heart rate of 200 and 200, and athlete A with the lower rate, the lower heart rate, was run at, say, 170, and athlete B at the higher rate maybe was at 190. Again, they both have a max heart rate of 200. That means that athlete A has 30 beats in reserve to increase velocity as needed. That's 200 as their maximum heart rate minus 170, gives them a 30 beat window. Athlete B, however, they have the same max heart rate, 200. If we subtract the heart rate at 190, that gives them just 10 beats. So in this theoretical race, athlete A should beat athlete B because they've got a bigger window to increase their oxygen delivery via cardiac output. The emphasis here is the stroke volume increases associated with training is a major advantage in sport.